Hello, everybody, and welcome to News from Hubble and Across the Universe. This is our monthly hangout where we get to meet with Dr. Frank Summers to discuss a lot of great new science and happenings in both astronomy and with the Hubble Space Telescope. My name is Tony Darnell. I work at the Space Telescope Science Institute with Frank, and welcome, Frank. It's good to see you again.
Good to see you, Tony. How everything been this last month? We haven't actually talked since July.
No, I know it's been a while since we've been doing this, so we got a lot to catch up on. But before we get started, let me remind everybody how you can interact with us if you want to leave comments or ask questions. We've got the Google Plus app, the Google Plus event page. We have the Q&A app on both YouTube and Google Plus, and I'm looking at the Hubble Hangout hashtag. Although we'll probably change that for future shows. But for right now, if you want to leave a tweet, Hubble Hangout is what I'm looking at. So, how many H's on that? It kills me every time. Anyway, so this month, Frank is back. Like as Frank mentioned, we missed last month for two reasons. I was on vacation. That was one, and another was we just couldn't get our stuff together in time to make it happen. So we are going to. We have a lot of things to cover, and Frank, I will turn it over to you to get us started.
Yeah, I will apologize that I was out of the country. I was up in Vancouver for a week, so August is a pretty busy month for vacations and travel and such. So we will do now a extra big show, extra cool stories for you today. Okay.
Cool. Yeah, there's some recent stuff that happened last month, I think, that you covered that you're going to also cover with us. So.
Exactly, and that's going to be my first story, okay? Because this happened just before I left for Vancouver. All right, so story number one, Rosetta, rendezvous with rubber ducky. Okay.
You really like that rubber ducky part, don't you?
Wait till you see. Wait till you see. You know all about this. All right. So first of all, this is about the Rosetta mission, and it's a mission to a comet, comet 67P Churyumov-Gerasimenko.
Good job.
That's a tough thing to say. As you can see pictured here, they've got the Rosetta is the spacecraft with the long wings on it. That's the Rosetta mission itself, and then they also have the Philae probe that is going to land on the comet. Okay, so it's a combination of a flyby as well as a probe landing on it. Although it's actually more than just a flyby. Okay, now we've been past a bunch of other comets before, and as you can see in this slide here, here are 6 different comets that we have visited, basically generally with flybys. And you can see they're about 5 miles across, from 1 mile to 9 miles across, and they've got these oblong shapes. And most of them are sort of roundish or potato-ish. Although I think Borley and Hartley, they could be bowling pin comets. All right, they look like bowling pins. But
yeah, my professor always called them oblate spheroids. But Deep Impact actually hit. We didn't just fly by, right?
Yeah, no, Deep Impact, we actually did a flyby and we did a smash in. So we did both a flyby and we didn't land gently, okay? That's the difference with this one. This one we're going to try and land gently. With Deep Impact, we actually tried to smash into it. We saw all the powdery stuff come out of it. So we've been there, we sort of know. But what we've never done is actually travel along with for an extended period. So this is what Rosetta is going to do. Here is the whole timeline, okay? You can try and read that. The font's probably too small to read over this. But the idea is that it launched in 2004, March of 2004. It got gravity assists from Earth, Mars, Earth, asteroid Steins, Earth again, asteroid Lutetia, so it's got like 7 different gravity assists in order to make its
gravity, huh?
An extreme exercise in celestial mechanics. Okay. But the point was, it arrived at the comet August 6th of last month. Now it's better to understand the orbits if you show it here. And so here you can see the orbital pass, and all of the early gravity assists were there to put it on a much more elliptical orbit so that it could match the orbit of Churyumov-Gerasimenko.
Does it take a lot of energy to get into an orbit like that, to an elliptical orbit?
Well, yeah, simply because Earth is on a circular orbit. When you launch from Earth, you're launching basically with Earth's momentum around the sun. And so you've got to change that momentum into a much more elongated orbit. So while as you can see, the red line and the green line are almost coincident at one point in terms of their perihelion, the closest approach to the sun, the aphelion is so much further away for Comet 67P that you've got to add a lot of energy to get it out to that, right?
Mm-hmm.
So the really cool thing about Rosetta mission is after it has met up with the comet, it's going to stay with the comet all the way through perihelion passage.
So it's not in orbit around the comet, it's just sort of tracking along in the comet's orbit.
Yeah, it's tracking along with it. It's doing a librating orbit near the comet, actually. Yeah. As I saw it described once, that it's in front of the comet. It's not actually orbiting around the comet. It's orbiting along with the comet. So it's on the same path at the same speed. Yes. And so you can see how difficult it is, and if you want to do it inexpensively, to do all this sort of stuff, the amount of energy that it takes to match orbits. Okay? So this is really cool. We have now matched up with the comet, and I was going to go through some of the images that we had of the comet approaching it. Okay, so this is the first image released this year, March 27th, and the main thing in this image is the globular cluster M107. Okay, so this is, I think it's in the constellation Ophiuchus. That's M107, and then what looks like just one of the stars of M107 or the stars nearby M107, that's actually the comet. Okay, so that circle is around the comet 67P. I'm calling 67P CG, just for.
I'm glad that circle's there. It'll make Rosetta easier to find.
Absolutely impossible spot otherwise. Then the next thing that was interesting that they released was on July 4th, on Independence Day in the U.S. This year. They released these three images here. And these three images show you that it's more than just a dot. It looks like sort of an elongated dot. Okay, and you can't really see it. It's all very pixelated and everything, but you're starting to see that, well, this is kind of interesting. It probably has that potato shape that we've seen for all the other comets, right? But they saved the best for French Independence Day, Bastille Day, July 14th, 2014.
Oh, the French get release.
Well, it is a European mission, right? So,
right.
So on Bastille Day, they released this image, and this immediately shows you that dark line of shadow center shows you this looks like two objects. It looks like two snowballs hanging around each other. Not one object. It looks like two objects together, which was really cool. And then everything really went crazy the next week. This sequence of images from July 23rd to 27th hit the internet, and everybody started freaking out. This wasn't just a single comet. This was a contact binary comet. All right? It was absolutely amazing. This is what I call Comet Rubber Ducky. Okay, not just me. A lot of people have called it Comet Rubber Ducky.
So you got to explain to us what a comet, a binary. What was it you said? Binary what?
Contact binary.
Contact binary. What is that?
Thank you for asking, because that's just where I was going to launch into.
Okay.
Well, all right. So the point is that it's obviously two separate pieces that have joined together at the neck of the duck. And in order for these things, now comets can be relatively fragile objects, right? Comets can be just sort of rubble piles or ice, as they're snowballs. If they came together too hard, they would smash and break up. Okay, and what the calculations were on this one was that for these two objects to stick together, they had to approach each other at a speed of like 3 meters per second. Now, 3 meters per second is fast for you and me, but in the solar system, that's actually quite slow, because Earth orbits around the sun at 30 kilometers per second. So in order to match up, these two objects had to be almost on exactly the same orbits and then just sort of gently smash in together and stay in contact with one another. So it's really interesting. We don't know how strongly they're held together. They obviously are held strongly enough to resist the rotational forces that might pull them apart.
Right, I was going to say that must be acting against it. So it's hard to imagine this is just gravity doing the sticking together, is it? Or do you think that's all it is?
Well, I mean, it's gravity plus there can be some chemical bonds, and what holds a snowball together, right?
Yeah, they kind of got squished together like packing a snowball. I think it melted a little bit and kind of stuck together.
I mean, you can consider this a solar system exploration in making a snowman.
Right.
You get a third one, okay, and then we can have a snowman comet, but I think that's highly unlikely to happen.
Yeah, that bringing that together would be impressive.
Okay, so this got everyone's attention on it. I think, from what I heard, some of these images were released prematurely. The science team behind it didn't want to release them until they really knew what they were looking at. But it was just so cool. Somebody had to put it out. And so the next week they actually released some earlier images from the OSIRIS team that actually had even higher resolution, and you can really see this double contact binary. So we were watching really closely as it was going into rendezvous, which was on August 6th. So here on July 24th, based upon that data, they made this animated GIF, this spinning 3D model. Okay, so a rough model of it, where you can see you've got a larger one that looks very much like the ones we got. We've got a smaller circular one. Again, the two of them separately look very much like the other comets we've seen, but then they get smashed together by this neck feature. All right, August 1st, we start to see all the detail in it. All of the cragginess that we saw in all the previous comets starts to come into view. We get a little closer daily. August 3rd.
Look at that.
I mean, that almost looks like a mushroom cloud type going off.
Yeah, really, it looks like he just got hit by an atomic bomb. The rubber ducky's out the window now. I don't see it.
Don't worry, rubber ducky will come back. Okay, this one had a feeling like a mushroom cloud. But what I loved about this one is it showed you the narrow features of the neck and how tenuous the connection is between them. Right?
Yeah.
It's as if they smashed together and rebounded, and you formed this bridge there, and then just no material was left in between on that. So that was really cool to me.
Yeah. It's almost like they kind of hit and then heated up, sort of merged and squished and melted a little bit. Then when they started to go apart, it froze. That's what I think happened, Frank. That's okay. I'll get the Nobel Prize later. I just wanted to say what I think it was.
All right. Well, that is a reasonable hypothesis. You just have to calculate what the speeds and the physical properties that would happen during that before you get your Nobel Prize, though.
Yeah. Emily, is she on the team?
No. I'll tell you at the end of this that I stole. The easiest place to steal all these images was from her blog. Okay?
Yeah, she's really great at that. Yeah.
She was really good. So, I got a lot of things from a lot of places, and it was just like to try and assemble it for this talk. It was like, we'll just go to Emily. And
she's got it. She'll know it. She'll have a deal.
She reprocessed a bunch of these images to clean them up and make them look better before posting on her blog. So she added her name to the credit list.
Very nice.
Actually, the credit lists are monstrously huge for this. Just some of these are. Anyway, so August 4th, again, you see some serious craggy and bumpy features and stuff. It's really, taking shape. It's starting to be a real object, okay? And then after August 4th, on August 6th, we had Rendezvous. And Rendezvous was successful. They did the insertion burn to slow down to get to the speed of the comet because they've been catching up to the comet. And then they slowed down, and they're in this librating orbit around it, basically in front of it, looking at it with the cameras. Well, after Rendezvous, they were so close that they were only getting pieces of the comet. They couldn't show you the whole comet.
Oh, the camera didn't have a wide enough field of view, huh?
Right. Well, you want to be that close because you got to scan places for where this lander is gonna look, gonna land, right? So they released a mosaic like this, okay, of 4 different images, and then they said to image processors, okay, here are the 4 images that we took that mosaic over the whole thing. How about if you go out and try and mosaic them together? Because as the orbiter is moving around it, the lighting is going to change, the comet's going to rotate a little bit, so it requires a significant amount of image processing to combine these guys together, right? And so a gentleman named Daniel Machacek put together this one from the August 31st mosaic, and that I think is really cool. And although it looks kind of mean, it certainly does look like a rubber duck there, don't you think?
Yeah, I guess so. I guess so. While you're talking about this, Frank, I want to interject a comment from Judy Schmidt. She's made a comment about what you're saying. She said, despite how the photos look and being a snowball, the comet is actually very dark in color. Always surprising to learn how dark some things are, like the moon is pretty much charcoal. So
that is correct.
Yep. Thank you, Judy. Good insight. That's true. This is what you're looking at, of course, is the reflections from the sun, but this is a pretty dark object.
Yeah, the standard thing is that a comet is as dark as the asphalt on the road. Okay, and that because it's been traveling around in outer space for billions of years, any particles that hit it, cover up all the quote snow. You don't see white snow on comets, okay? Because the outer layer is sort of this tarry, gooky stuff. The inner layers are white and bright and would be your snow-like substances. But the outer layers have definitely been baked in the solar heat. All of the volatiles on the surface have evaporated away, leaving behind this sort of tar-like residue. Okay, so there's your rubber duck. Okay, but here's the question, and the question that they're studying this month is where on this rubber duck are they going to land? Okay, where are they going to put that lander?
The beak.
The problem is that because it's got this irregular shape, the orbit around it is actually not that difficult. It's just an irregular moment of inertia to work with. But now you've got to try and land on this while it's rotating with this kind of irregular shape. So that sort of limits some of the places that are possible to land. And so the plan was to come up with 5 potential landing sites toward the end of August, which they did. And here is a refined 3D model and with the 5 potential landing sites for the Philae lander. Obviously they chose a lot more because they got A, B, and C, but then they have I and J.
Yeah, I think
I don't know what
got dismissed.
D through H seem to have disappeared.
Didn't make the cut. Yeah.
Didn't make the cut. All right, so these are the 5 potential landing sites,
Cool.
And then they released some high-resolution photographs of those landing sites. So here's the A, B, C, I, and J landing sites. The scale on this is 1 kilometer. On a side for each of these, right? So that's really interesting, okay? I actually look at these pictures, and my favorite landing site might be Site B because it looks much sort of like a lunar mare, very smooth.
Yeah, I was going to say the same thing. I predict that's what they'll. I think it's B. B should be the one. The other ones look too scary.
Yeah, but what they're going to do is they're going to survey these 5 sites at a resolution of what they said, like, half a meter per pixel, which is amazing. But since they're that close, they will look at these sites in great detail at about half a meter per pixel resolution, and then before they choose their primary landing site. And I'm told that their primary landing site will be chosen in mid-September. So we got a couple weeks before we'll find out what the primary landing site is.
So let me ask you this, Frank. The spinning of the comet and the rotation and the fact that they found out this thing is not a very regular object, does that substantially complicate the orbiting or the landing equations that are going to be needed, or the trajectories, or are they concerned about that at all? Do you know?
Well, they very quickly, when they made the initial models of it, from what I understand, they recognized that they couldn't really land on the neck, okay? Just because of the way the rotation of it, trying to get into the neck might not be a really good spot. Okay, so I guess if I go to the previous one, you can see that they've got 3 sites that are on the top of the head, and then they've got 2 sites on what I would call the tail of the duck. Okay.
They're going to land on his butt. Site C.
All right. So landing on the ducky's tail or landing on the ducky's head seem to be the favored sites, both in terms of the orbital mechanics of it and perhaps in terms of the smoothness of the site for a landing. Right.
That is awesome. Yeah, neat.
So here is a point where I say amazing things about Ms. Emily Lakdawala.
One can never say too many.
Yeah, so she writes a blog for the Planetary Society, and I just want to give her a tip of the hat, not a wag of the finger, a tip of the hat, because it was easy just to go through a lot of her blog posts and pull out images for this. I will note that the landing for Philae will occur starting on November 11th. The orbital maneuver will start on November 11th, and it will land on November 19th. So for Thanksgiving, we may be serving duck. Okay.
In rubber form.
Rubber duck for Thanksgiving. Okay.
Nice. Well, that's great. No, and Emily is an outstanding resource for anybody who wants to keep abreast of the absolute latest. Her Twitter feed is also really a good source. I follow it, and I learn more from that about that. That's always, like Frank, one of my first choices to go to. So.
All right.
Yeah,
So that's story number one. I got three more, which are a little bit shorter on this, and then we actually, and in these ones, we actually get back to Hubble because there wasn't really a Hubble tie-in for Comet Rubber Ducky there.
No, Hubble's not looking at it.
Okay, so our second story today is big bursts of star formation in distant dwarf galaxies. Now, what we're really talking about here are starbursting galaxies, okay? Galaxies that have these immense amounts of star formation. And one of the prime examples to point to is the Antennae galaxy shown here. You can see there are two heads and then these two long tails that go off from each other. These two galaxies were determined about almost, it was the 1970s, so that's 40 years ago. It was determined that these two galaxies have been on a collision. Okay,
but longer than 40 years.
Yes, the collision lasts about 1 billion years. But it was 40 years ago when the Toomre brothers were actually able to deduce and show from computer simulations, very, very, very simple computer simulations back then, that the two galaxies were actually in the fact of colliding. And we believe that the collision incites star formation. And that star formation is greatly seen when we go to this Hubble image of just the central part of it, and you can see all those bright pink regions, which are star-forming regions, and all those bright blue stars, which are hot, newborn, massive stars.
So all those pink regions are areas where stars are currently being born within this collision.
Right, and they are regions that make the Orion Nebula look puny. All right. Now, the Orion Nebula is one of our closest and our most favorite star-forming regions. It's got like about 4,000 stars forming within it. These are superstar clusters that are forming here with tens of thousands of stars and lots and lots of stars in their formation. So these are really big. These are big star-forming regions. There's a ton of star formation going on in here, and that's what defines a starburst. Okay.
Are there any preference to the kinds of stars being born here? Are they a specific type of star, or are they just all kinds?
No, we've found that when you form stars, you tend to form stars of all different masses. You form you form a few really big, massive stars, and then a lot of faint stars. I think the average size of a star in a star-forming region is only 7/10 of the size of the sun. Stars can go up to hundreds of times the size of the sun and down to about a tenth the size of the sun, but the average mass is about 7/10 the size of the sun. So for all the really big stars that you can see here, there are lots more small stars that, of course, you can't see. So starbursts, we believe, are induced by an event. Normal galaxies just don't have this much star formation going on. Here, the event is the merging of two galaxies. So we wanted to, when we've studied starbursts, we want to actually study the star formation history of the universe. And these starbursting galaxies are the easiest ones to study because they've got so much star formation going on in them. And as we looked out into the distant universe, we used these deep images from Hubble. We've been able to study starbursting in the big galaxies and even some of the medium-sized galaxies. So as we look out into the universe and the formation of stars, and we find that the peak of star formation was about 4 or 5 billion years after the Big Bang. Okay, we sort of look in the redshift range 1 to 2, which is about 2 billion years after the Big Bang to about 6 or 7 billion years after the Big Bang. Okay, so that
was the period when most of the stars in the universe were born.
Exactly. Okay, so those are sort of the peak of star formation in the universe, and so we've looked at the star-bursting galaxies in those range, but only the medium and large ones. And with the Wide Field Camera 3, and in particular the increased infrared sensitivity of WIFC-3 on Hubble, we've been able to extend those studies to sample the smaller galaxies. And so this image here, there are 6 red circles around 6 of the small dwarf galaxies that they found to be starbursting. Okay, and they were able to study these dwarf galaxies having starbursts between 2 and 6 billion years out there. And that's really important because dwarf galaxies are the most numerous galaxies in the universe. Just like I said that, there are many more smaller stars than there are big stars, there are also many more smaller galaxies than there are big galaxies. So if these dwarf galaxies are undergoing starbursts as well, then they could have a significant effect. And it turns out that they have a really huge star formation, that they can double the number of stars in them within only 100 million or 150 million years.
So wait, why is that? So why is that so significant? Because dwarf galaxies are the most common type of galaxy, or they're the most numerous of the galaxies.
Exactly,
they're the most. If they're showing a lot of rapid star formation, then there's a lot more stars than we think there are. Maybe. Exactly.
If only 10% of your population is doing something, right? Well, then that sort of says, well, it's a good subgroup, but it might not be able to dominate what's really going on. But if 90% of your population is doing something, well, then just by sheer number, they can dominate. I guess we could relate it to the post-war generation, right? The baby boomers, how they've had so much population here in the U.S. and they've been able to dominate culture as they go through their lives, and et cetera. So you want the most massive population, find out what they're doing, then you'll get a better handle on what's overall happening, right?
Well, I don't mean to put you on the spot here, and so if you don't know the answer, that's okay. But do you have a sense of how many in terms of percent? Is it like 10% more stars, 20% more stars than we thought, 50% more stars?
I'll get to that. I'll get to that number at the end of this.
Okay, good. I don't want to steal your punchline.
I'm not going to give you my punchline until I'm ready for it.
Fair enough.
But we're very close to this. Okay, so these are in the range of what we call extreme emission line galaxies, EELGs. Okay, we're measuring their star formation by looking at the hydrogen alpha line. Okay, so the amount of hydrogen emission that's coming on there, which we found to be a very good measure of star formation, and that they are producing stars 100 times more rapidly than normal galaxies, and even several times more rapidly than our normal starbursts in the large galaxies. So when you add up all of these dwarf galaxies and the extreme starbursting that they're going through, they calculate, well, depending on how you do things, they could cover about 13 to 34% of the star formation going on between 2 and 6 billion years after the Big Bang. So they can account for up to 1/3 of all the star formation happening at that time. Previously, we didn't have any information on the dwarfs, and should the dwarfs be, they're awfully small, they're down to like 1% the size of a big galaxy. Should they really be considered? Well, the answer is yes. It's very surprising just how much they might contribute.
Okay, so let me just go back for a minute here.
Sure.
We've all seen this pie chart of the composition of the universe where all the matter that we know in the universe is like 4 or 5%. Dark matter makes up 20 or some odd 25%, and dark energy makes up the remaining 70%. What effect is this going to do, if any, on that 5% slice of pie?
Okay, so that 5% slice of pie will stay the same. Okay, it's not changing the amount of baryonic matter in the universe, the normal matter in the universe, right?
So
But what
that's conserved then, I guess.
okay,
It's okay.
that doesn't have an effect here. What this does have is, where do the stars that we see today get born? Are they born in large galaxies? Are they born in medium galaxies? Or are they born in small galaxies? What this result is saying is that up to a third of them may be born in small galaxies.
Good.
All right,
and then if they, I wanted to make, because I don't want people to think we've discovered a whole bunch of stars that we didn't know were there before. It's all we're getting a better idea of where and how these stars are forming and when in the history of the universe. Right?
Exactly.
Okay.
We know that we can approximate the stellar content of the universe today, and we're trying to figure out when did they form and where did they form. We figured out when they formed, it appears, but now we're seeing that more of them form in small galaxies than we had previously suspected.
Awesome.
All right.
Thank you, Frank.
That's cool. That is that story. And we're going to move on to another star-bursting object. We're going to talk about a baby elliptical. We've talked about rubber duckies. Now we're going to go a cute little baby elliptical galaxy here. So when we think of ellipticals,
I didn't know there was such a thing, to be honest.
Well, you've never seen one before. That's the point of this story, okay? When you think of ellipticals, you don't think of cute little objects, okay? Maybe there are some dwarf ellipticals that are small.
Yeah, they're the largest galaxies in the universe.
Right, okay? So this image here is of the Perseus cluster of galaxies, all right? And because it's far away, right, most of the galaxies here are roughly the same distance. So you can actually compare sizes one to another. And you can see that the largest ones here are these elliptical galaxies near the center. You can pick out a few spiral galaxies in here, and they're all considerably smaller. So you've got these giant elliptical galaxies, okay?
I'm sorry, did you say how far away this cluster was?
I did not. I actually just wanted to use this as an example of giant ellipticals.
Oh, okay, okay.
They're all
about the same. They're all about the same distance.
All about the same way, very far away. They're hundreds of millions of light years away. How about that?
Yeah, okay.
All right. And so we got these giant ellipticals, and we believe that since they existed, that we find them a lot at the cores of clusters, that they accrete their mass by merging. Okay, I showed you one image of merging previously, but at the center of a cluster of galaxies, you would naturally get more merging, and that was where you find these giant ellipticals. But, so we can see how they grow, but we wanted to know, how do these giant ellipticals start? These galaxies that become these big galaxies, how do they really start? And we can look back out into these deep images. All right, we can take a look at this is a galaxy in the Coma cluster, an elliptical galaxy in the Coma cluster, and so they have these dense cores at their center. All right, and we believe that these must form relatively early on in the universe, okay, because you've got very old stars in here. And we can account for growth via merging, and we can look out into the universe and trace them back. But what we really wanted to find is that formation of that core, right? And we hadn't been able to see that yet. Okay, we wanted to find the formation of that initial core, which probably grew very, very fast. Well, we did one of these deep images of the universe, searching for this, and again, using the infrared capabilities of WIFC-3, just letting you know that the infrared is proving to be extremely useful on WIFC-3. They identified this object here, this orangish object here, as being a really good candidate for being the core of what would become a future elliptical galaxy. Now, what are the special characteristics of this object that make it a candidate? Well, it's really tiny. It's about 6,000 light years across, whereas a galaxy like our Milky Way is 100,000 light years across. 6,000 versus 100,000. So this is smaller even than the bulge of our Milky Way galaxy, the core of a large galaxy. It's smaller than that. But already this object has as many stars in it as are in our entire Milky Way galaxy. So it's a ton of stars compressed down to a very small region. Furthermore, this object is seen at a redshift of 2.3, which places it at 3 billion years after the Big Bang, or about 11 billion years ago. So this is an object that happened very early in the universe, formed a ton of stars into a very small region. They measured, and they able to measure the star formation rate going on in here, and again, intensely high, another star bursting thing. And looking at the history of it, trying to gauge the ages of things so that they could try and interpolate the history of it, they figured it probably had to have been going on for about 1 billion years. So you're talking an intense star formation rate for about 1 billion years. Now, it wasn't just Hubble that was involved in this study. That star formation rate from Hubble would have actually been about 1/6 of the star formation rate I just quoted to you. Instead, they used observations from the Spitzer Space Telescope and from Herschel Space Telescope to look deeper into the infrared than Hubble can see, and find more information and the deeper infrared wavelengths that showed that the star formation rate was actually higher than we would have deduced from just Hubble's observations. Actually about 6 times higher. All right. So by having this incredibly high star formation rate and not being able to see it with Hubble, the implication of that is that there's a lot of dust obscuring this galaxy, okay, or this core of a galaxy. So the postulation, the conclusion really, is that the reason we haven't seen these before is that we haven't, that they are highly obscured with lots of dust. There's a tremendous amount of star formation kicking up lots of dust within this galaxy. They're heavily reddened and obscured by this dust, and so we're not going to see them very well with visible or with near infrared light. We need a little bit longer infrared light to be able to penetrate through some of that dust and be able to find more of these cores of elliptical galaxies.
Which James Webb will be able to do pretty well.
Oh, you go straight to the punchline there. Yeah, there we go. That's the conclusion that we have to jump to, right? Right. No, simply because we're going to need the longer wavelength. JWST will have the infrared wavelengths. It will have the resolution of Hubble. It will be able to see objects like this much more easily than either Hubble or Spitzer or Herschel.
Okay. So we got an elliptical here. 3 billion years after the Big Bang. It's been burning. It's been forming stars for about 1 billion years.
Yep.
Give us some context. Compare that with our Milky Way. How old is our Milky Way galaxy, and how
Let's see. The basic core of our Milky Way galaxy, the basic disk of our Milky Way galaxy, we believe is about 9 or 10 billion years old. So about 1 billion to 2 billion years after the core of this elliptical galaxy formed would be when the basic structure of our Milky Way formed.
But wait a minute. So we've got a galaxy that's very old, and we're still a spiral. I thought ellipticals were among the oldest, and they were the result of a lot of galaxy collisions that ultimately did not have stars forming in them. And you've shown us an elliptical that does have stars forming in them. So the processes can't be the same, right? This elliptical wasn't formed like most ellipticals.
Well, this elliptical was formed very early. It started its formation very early, and had and could not have formed in a low-density quiescent way. Okay, if a galaxy forms quietly, and things slowly drift onto collapse onto it, right? The angular momentum of the collapse is going to naturally produce a disk. All right, so spirals form in a relatively quiet fashion.
Okay.
If you form in a very dense neighborhood, when you get lots of small subclumps that gather together and smash together,
like the early universe.
Right, the earlier universe, which was denser, right? Then you're going to naturally get a more randomization of your orbits, and you'll end up with elliptical shapes.
Awesome. All right. Thank you. Yeah, that makes. I understand. That's cool. Thanks.
Okay. So the main question that we want to be able to answer is just how many of these exist, how prevalent are these, can we get lots of baby elliptical galaxies, and can we really study this as a group? Because if you have one object, okay, that's great. That's a nice tick mark. You can, but can you extrapolate from that into the characteristics of a group? No. You want to be able to get a group of these, and that is something that we will definitely study with the James Webb Space Telescope.
Okay.
All right.
All right. Let me just, before we leave this topic, Judy has another question, and I just want to, since it's relevant, I'll bring it up. Judy Schmidt, does this bring us any closer to understanding the origins of globular clusters? I meant this question in reference to the dwarf galaxy study.
So in terms of the understanding of globular clusters, that's a special topic, okay? Because globular clusters can have hundreds of thousands to even millions of stars. And we know that the globular clusters in our Milky Way galaxy are all very old, all generally very, very old, and that there was a special formation process for these globular clusters about 12 billion years ago. All right, so even a little earlier than this galaxy that we see here. And we've also found that we believe that when you see evidence of mergers, you also see a higher number of globular clusters. So that globular clusters seem to also be formed during mergers. So the merging sequences can obviously incite the kind of conditions that form globular clusters. So the formation of a globular cluster seems to be an extreme version of star cluster formation, and we're not exactly sure what the characteristics are of that. It's still actively under study, and this shows us as on a much larger scale in terms of the number of stars here. So it gives us some implication in terms of when the galaxies start forming, but the globular clusters that are small parts of those, it doesn't quite tell us anything about that. Okay?
Awesome. Thank you, Judy.
All right. So our final topic for today, a space oddity. All right, and I'm going to start with an image that you may have seen before. Actually, I hope you have seen before. It's a cool image of a galaxy cluster called Abell 68. And Abell 68 is one of those gravitational lensing clusters. All right, and if you don't know what that means, Einstein's theory of general relativity tells us that mass warps space. Actually, that's my favorite three-word summary of general relativity. Mass warps space. Okay? That's all you need to know about general relativity. But in this case, there's so much mass here in this cluster of galaxies that it warps space so much that the light passing through that space changes and diverges. Okay? It acts like a lens, and it redirects the light from galaxies that are on the far side of this cluster. And there's a really cool effect that happens. You can see there are a bunch of streaky things around this cluster, long, thin things. That these are galaxies that are behind the cluster whose light has been stretched out into these long, streaky things by the gravitational lensing of the cluster. But there's also this object right here that I put a box around, okay? And if we blow that guy up, you can see it's got a really interesting shape.
Yeah.
Matter of fact, it doesn't belong in a galaxy cluster. It looks like it belongs in a 1970s video game.
Yeah, I knew you were going there. Yeah. Definitely Space Invaders.
So this we call the Space Invader Galaxy. But, of course, it's not a Space Invader Galaxy. This is not its true shape. It's been gravitationally lensed. You can see the two yellow dots that form the eyes of the Space Invader, right? Mm-hmm. Well, that's the same yellow dot, but traveling two different paths through the mass of the cluster, through this warped space around this cluster. It's doubly imaged so that you can see there's sort of a mirror reflection left to right of the features of this galaxy. So the galaxy's features have been warped, they've been changed, and they've been mirrored so that you see two mirror images of it, and then you get this beautiful Space Invader
it
type
also
shape.
looks like, I don't know if you ever saw a movie in the 1980s called Krull. It was this really kind of cheesy fantasy movie. It looks like the bad guy in that. He had really big horns, and it kind of looks like horns sticking out of his head and everything else. That's kind of what it looks like. It reminded me of that too.
Okay. Well, you could definitely use this as a bad guy in a movie. Right, but Abell 68 has more interesting features than that. There's another oddity in Abell 68 that I wanted to point out. So that one was gravitational lensing, but this one over here in the upper right, you can see this galaxy here. Now let me pull that up in big. All right, and you can see this is a galaxy where it looks like it's raining, right? You've got all these sort of droplets coming down from the galaxy. And we're looking at that. I have to mute my phone. Anyways, it looks like it's raining down, and then that looks really strange too. That's an oddity. What's happening here is not gravitational lensing. Instead, the galaxy is moving through the intercluster gas. There's lots of gas in between these galaxies, and that gas is actually ram pressure stripping material out of this galaxy.
That's amazing.
Yeah, so what looks like teardrops falling from this galaxy, this crying galaxy, is actually material just being stripped. So as you're moving through this dense intracluster medium, some of the gas is being stripped, all right, and we're getting star formation in that stripped gas, forming these wonderful, wonderful little raindrops coming out of the galaxy, or tears flowing down from the galaxy.
It's a sad galaxy.
So this is a really cool image here in Abell 68 in that you get to see both a gravitational lensing oddity as well as a physics-based oddity. Okay, so with Hubble, we're doing a study looking at gravitational lensing clusters, and in one of the clusters, they saw this. And here you can see this is a cluster that's producing gravitational lensing. If you look carefully, you can see some streaks and arcs. You can especially see this almost circular grouping of streaks and arcs around the central center of the cluster. And you say, wow, that's a lot of gravitational lensing going on here, right?
Yes.
So when you look in the center and you see these blue crazy little archy things, you immediately think, well, that's got to be gravitational lensing, right? It's not. They did a study with another telescope in the radio telescope to look for it, to try and look at the details of it, and they proved that it's not gravitational lensing, which makes you go, whoa, okay, now what are we gonna do with this? Because where are you gonna get these bright blue, sort of spiral-shaped, really long, elongated knots of what look like bright stars here? Okay, so let's just look at it phenomenologically first, okay? This thing is about 100,000 light years long, right? That's stretching from side to side all the way across the Milky Way galaxy. So this is a galactic scale streamer. Plus, it's got some spiral shape to it. It's got a bit of a coil shape, and it seems to be wrapped in amongst these two colliding galaxies. So you've got a lot of this long, thin streamer with this spiraling shape, all right, and then you've got these knots along it. And if you analyze those knots, they believe that these knots are star clusters. Not just star clusters, but superstar clusters, like the big star clusters that we saw in the antennae galaxies. So it's really kind of cool, all right, that you've got this amazing structure. And they wanted to do an analogy for it for the press release, and so they took the analogy, well, the physical process behind this is what we call the Jeans instability, okay? And the Jeans instability governs when a cloud of gas becomes self-gravitating and collapse down to form stars or star clusters, okay? And so when you get a Jeans mass of material, then it can become self-gravitating and unstable to forming stars and clusters, right? But that's kind of in this long, thin streamer, you would have separate regions that reach Jeans mass criticality and then would start to collapse, and that's how you would get these knots along the streamer. So the analogy that they used in the press release was with the water coming out of the faucet in your kitchen sink. If you have a smooth, very thin laminar flow leaving your faucet, at some point it's going to collapse in upon itself and form water droplets. Okay? This is a well-known physical effect. And it has a similar analogy of the physical effects as to the formation of these clusters along the long, thin streamer of gas. Now, I have to be totally honest with you, it's not an exact analogy in terms of physics, because the water involves the turbulence within the water and the Reynolds number, as well as the surface tension of the water also plays a very important role. And you've got a gravitational field that's within. So it's not a perfect analogy here, but it's a useful visual analog for you to understand that these physical processes that happen in your kitchen sink can also happen on scales of entire galaxies. And that's a lot of fun.
Yeah.
Right?
There was just a time when everybody thought that everything happened up in the sky the universe was a very static place. It never changed much. And with over the past 25 years with Hubble and even other, so many other instruments, we're learning that God, the universe is like completely on just fire. It's just doing all kinds of things, and it's far from static. So yeah.
And and educationally, it's a fundamental lesson of science that what happens here on Earth happens elsewhere in the universe. That's sort of an assumption we make in science. But this is the got to be the biggest scale change, one of the biggest scale change possible, going from your kitchen sink all the way to the scale of an entire galaxy, using the same sort of physics, showing that hey, the physics equations work here, they also work there. That's a nice perspective on the universe.
I think it's amazing. What did you say? Did you say how far away this was? What were the?
I did not. I've got the press release in front of me here. Zoop.
It's just not that critical. I was just trying to get a sense of how far back, after the Big Bang this was. So.
Yeah, it's not that far. It's not. These aren't high redshift clusters. So I would say they're definitely less than a redshift of a half. So there may be a couple billion. This is probably a couple billion light years out there. It's not going to be 10 billion light years. It may be 2-3 billion light years out there.
Okay. All right. I was just curious. Yeah, it was because the universe was a lot different at high redshift than it is in the lower ones, and so one can imagine maybe things not working, the analogy not working out even more so back then. But it sounds like that's not the issue here.
No, this is rough enough to be considered the local universe. Okay.
Okay. Did you have another slide?
Okay. I had actually just one last question to pose about this.
Okay.
Why? How do you get
a bad galaxy?
No. How do you get a 100,000 light year long streamer of gas? All right, no matter what its shape is, no matter what it's done, how do you get that?
I'm going to say black holes. That's my answer to everything I don't understand.
All right. The answer is that we don't understand it. Okay.
My answer.
There are 3 possibilities mentioned in the press release. None of them are compelling. Okay. How does material collapse? You can come up with an idea that material should cool down towards the center of a cluster of galaxies, but that doesn't form it into a streamer. Okay, you could say that this is maybe the remnant of a tidal tail wrapped around these galaxies, but the kinematics of that doesn't really quite work. Why is it wrapped in between the galaxies and such? There's going to be a lot more study to understand this.
So wait, how sure are they that this is actually not some kind of illusory effect with the line of sight or something? Are they sure these droplets or these blue dots are intertwined?
I would believe that since they are star clusters, they have emission lines, and they can redshift the emission. They can look at the redshift of the emission lines. They can look at the redshift of the galaxies and make sure that they're the same.
Okay, all right. So they do have sort of a 3D structure to this then by looking at the spectra.
Okay. So this is one of my fun points to make, is that we don't know the answer, and you know what? That's not bad. That's actually really good. Okay, 1, it's job security for us, right?
Right.
But 2, when you see something like this, it's your indication that, hey, we don't know what's going on. There's something new to understand about the universe. We love confronting our ignorance because it shows us there's something new to understand. Okay.
Yeah, I think, was it George Gamow or somebody back in the day said, we know just about everything there is to know, or at least we will in about 2 years.
People have said that over the centuries,
Yeah,
and they've always been so wrong.
we figured it out already. We know most things.
Okay, so I put up the slide that we said we would do
Yep.
about the upcoming public lectures.
So
Go ahead.
they just wanted to point out to everybody that this little hangout that Frank and I do every month is in conjunction with the Hubble Public Lecture Series that we have on the first Tuesday of every month. But Frank, September 18th isn't the first Tuesday.
Not the first Tuesday. We've got a special lecture for you. Ray Jayawardhana from York University is coming in. He's giving a colloquium here, a scientific colloquium, and he also agreed to give a public lecture on that Thursday. So I said, great, we'll add you to the schedule, and we'll have an amazing talk on neutrino hunters, the ghostly particles of neutrinos that, you know, you've got 1 billion neutrinos passing through you every second right now, and you don't feel anything. But we can also use these neutrinos to unlock cosmic secrets, and he will talk about that.
Awesome.
And then, of course, our regular one, first Tuesday of the month, October 7th, Greg Snyder will talk about simulating the universe, the illustrious computational simulation, one of the largest computer simulations of how structure forms in the universe. He is part of that team, and he will tell you all sorts of secrets of how to make a fake universe and see if it matches the real universe.
Yeah, I'm really excited about that one, because if you haven't heard of this, do a search for it on Google, and it'll come up. There's a YouTube video that Nature put out that shows this simulation too. It's just amazing. You've got to check. It's one of the neatest things I've ever seen in a long time. So, in addition to checking out the public lecture next month, definitely do a search on that. If you haven't seen it yet, it's mind-boggling. So, okay, Frank, we have a couple of questions here. I want to get to a few things. We're running out of time, but I'll start with an easy one. This one's from Angel Lights 3. How long does the Hubble take to do a complete rotation around our Mother Earth?
Okay, Hubble orbits around Earth every 97 minutes. If you watch the movie Gravity, they put it at like 90 minutes, right?
Yeah.
And it's actually 97 minutes at the orbit of Hubble.
To be fair, I always say 90 minutes. But
yeah, it's approximately 90 minutes. So we've been talking for almost an hour. Hubble has completed 2/3 of an orbit around the Earth while we've been chatting here.
Yep. Good question. Okay. Here's one from. We're getting some questions on this. I'll start with Stargazer Nation. What is next for the telescope? Any upcoming highlights? I wonder how close it would focus, and are they going to see Siding Spring? There's a couple of questions about that, and if you had any news on Siding Spring on that as well. So,
okay. First of all, Hubble will be observing Comet Siding Spring. The Comet Siding Spring is going to pass close to Mars. The information on Comet Siding Spring is that its coma is not growing as fast as one might have thought. So the coma of Comet Siding Spring, which I never thought was actually going to encompass Mars, doesn't look like it's going to encompass Mars, although the density falls off very, very slowly. So definitely some particles traveling with Comet Siding Springs will impact Mars, but the risk to the Mars orbiters, etc., is a little lower than might have been feared. Hubble will be looking at the comet itself because Hubble has the best resolution of any telescope here located at Earth, and so we can't see the size of Siding Springs. It's so small. We'll be able to see if any pieces of it break off, anything happening with the comet. Hubble will be monitoring it during the closest approach, and it comes up in October, doesn't it?
I think so. Yes.
Yeah.
So, okay, and that is also Janine Bevan, also from the Q&A app, was asking about Siding Spring. So there you go, folks. Good questions. And here's one from Eamon Fanton, who's asking, where'd it go? I clicked on it and then it went away. Come back. Okay. All right. Fine. So. So Janine was also saying, lol, now I'm sitting at my desk humming along to Rubber Ducky. Thanks, guys. Rubber ducky, you're the one. You make
astronomy so much fun.
That's right. Now we get to all sing it. Thank you for that. Yes, rubber ducky.
Okay.
I don't know what happened to that question. It had to do with exoplanets, but it disappeared from my Q&A app. I'm really sorry about that. I guess that'll be, so that is it for our time. I don't see any other questions or comments that I should read out. Thank you all for watching for participating, doing the Q&A app. I really appreciate that. We will be back again next month with Frank. Well, no, September. Are we going to do this again this month, or are we going to just wait till October?
Well, we're already into September. This is September 3rd.
Well, I know, but we had another public lecture, so I don't know if you wanted to.
I wasn't planning on doing a huge news summary for the September 18th.
Okay. All right, then we won't worry about that. We'll just
if something amazing happens with Siding Springs or anything, we can jump in and do that. Actually, I'll be my son's going to college.
Okay.
Late September, so we'll have to do it in October. Okay.
So look back for the next episode of this with Frank at the beginning of October, right after the public lecture series we just talked about. I want to thank you, Frank. This was awesome as always. You've done an excellent job bringing some awesome stories to us. So thank you very much.
You do an excellent job of asking questions and keeping me honest about it.
That's my job. That's what I do.
All right.
All right, folks. Anyway, thank you all for watching. And as always, keep looking up.
We will do now a extra big show, extra cool stories for you today, okay?
Cool. Yeah, there's some research stuff that happened last week or last month, I think, that you covered that you're going to also cover with us. So.
Exactly, and that's going to be my first story, okay? Because this happened just before I left for Vancouver. All right, so story number 1, Rosetta, rendezvous with rubber ducky. Okay.
You really like that rubber ducky part, don't you?
Wait till you see. Wait till you see. You know all about this. All right. So first of all, this is about the Rosetta mission, and it's a mission to a comet, comet 67P Churyumov-Gerasimenko.
Good job.
That's a tough thing to say. As you can see pictured here, they've got the Rosetta is the spacecraft with the long wings on it. That's the Rosetta mission itself, and then they also have the Philae probe that is going to land on the comet. Okay, so it's a combination of a flyby as well as a probe landing on it. Although it's actually more than just a flyby. Okay, now we've been past a bunch of other comets before, and as you can see in this slide here, here are 6 different comets that we have visited, basically generally with flybys. And you can see they're about 5 miles across from 1 mile to stand the orbits if you show it here. And so here you can see the orbital pass, and all of the early gravity assists were there to put it on a much more elliptical orbit so that it could match the orbit of Churyumov-Gerasimenko.
Does it take a lot of energy to get into an orbit like that, to an elliptical orbit?
Well, yeah, simply because Earth is on a circular orbit. When you launch from Earth, you're launching basically with Earth's momentum around the Sun. And so you've got to change that momentum into a much more elongated orbit. So while as you can see, the red line and the green line are almost coincident at one point in terms of their perihelion, the closest approach to the Sun, the aphelion is so much further away for Comet 67P that you've got to add a lot of energy to get it out to that, right?
Mm-hmm.
So the really cool thing about Rosetta mission is after it has met up with the comet, it's going to stay with the comet all the way through perihelion passage.
So it's not in orbit around the comet, it's just sort of tracking along in the comet's orbit.
Yeah, it's tracking along with it. It's doing a librating orbit near the comet, actually. Yeah. As I saw it described once, that it's in front of the comet. It's not actually orbiting around the comet, it's orbiting along with the comet. So it's on the same path at the same speed. Yes. And so you can see how difficult it is, and if you want to
Hello, everybody, and welcome to News from Hubble and Across the Universe. This is our monthly hangout where we get to meet with Dr. Frank Summers to discuss a lot of great new science and happenings in both astronomy and with the Hubble Space Telescope. My name is Tony Darnell. I work at the Space Telescope Science Institute with Frank, and welcome, Frank. It's good to see you again. Good
to see you, Tony. How everything been this last month? We haven't actually talked since July.
No, I know. It's been a while since we've been doing this, so we got a lot to catch up on. But before we get started, let me remind everybody how you can interact with us if you want to leave comments or ask questions. We've got the Google Plus app. We've got the Google Plus event page. We have the Q&A app on both YouTube and Google Plus, and I'm looking at the Hubble Hangout hashtag, although we'll probably change that for future shows. But for right now, if you want to leave a tweet, Hubble Hangout is what I'm looking at. So too many H's on that. It kills me every time. Anyway, so this month, Frank is back. Like as Frank mentioned, we missed last month for two reasons. I was on vacation. That was one, and another was we just couldn't get our stuff together in time to make it happen. So we are going to we got a lot of things to cover, and Frank, I will turn it over to you to get us started.
Yeah, I will apologize that I was out of the country. I was up in Vancouver for a week, so August is a pretty busy month for vacations and travel and such. So do it inexpensively to do all this sort of stuff. The amount of energy that it takes to match orbits. Okay, so this is really cool. We have now matched up with the comet, and I was going to go through some of the images that we had of the comet approaching it. Okay. So this is the first image released this year, March 27th, and the main thing in this image is the globular cluster M107. Okay, so this is, I think it's in the constellation Ophiuchus. That's M107, and then what looks like just one of the stars of M107, or the stars nearby M107, that's actually the comet. Okay, so that circle is around the comet 67P. I'm calling 67P CG, just for.
I'm glad that circle's there. It makes it'll make Rosetta easier to find.
Absolutely impossible spot otherwise. Then the next thing that was interesting that they released was on July 4th, on Independence Day in the U.S. This year. They released these three images here. And these three images show you that it's more than just a dot. It looks like sort of an elongated dot. Okay, and you can't really see it. It's all very pixelated and everything, but you're starting to see that, well, this is kind of interesting. It probably has that potato shape that we've seen for all the other comets, right? But they saved the best for French Independence Day, Bastille Day, July 14th, 2014.
Oh, the French get release.
It is a European mission, right? So
right.
9 miles across, and they've got these oblong shapes, and most of them are sort of roundish or potatoish. Although I think Borley and Hartley, they could be bowling pin comets. All right, they look like bowling pins. But
yeah, my professor always called them oblate spheroids. But Deep Impact actually hit. We didn't just fly by, right?
Yeah, no, Deep Impact, we actually did a flyby and we did a smash in. So we did both a flyby and we didn't land gently, okay? That's the difference with this one. This one we're going to try and land gently. With Deep Impact, we actually tried to smash into it. We saw all the powdery stuff come out of it. So we've been there, we sort of know. But what we've never done is actually travel along with for an extended period. So this is what Rosetta is going to do. Here is the whole timeline, okay? You can try and read that. The font's probably too small to read over this. But the idea is that it launched in 2004, March of 2004. It got gravity assists from Earth, Mars, Earth, asteroid Steins, Earth again, asteroid Lutetia, so it's got like 7 different gravity assists in order to make its
gravity, huh?
An extreme exercise in celestial mechanics. Okay. But the point was, it arrived at the comet August 6th of last month. Now it's better understood